In this video, we will talk about what a cross product is. So in the last section, we talked about dot products. Dot products, in a rough sense, were a way to multiply vectors. The cross product is another way to multiply vectors in a rough sense. So let me state the definition. So the cross product of two vectors, u and v, which is written u, in fact, let me write written better. So written u, and then we put an x, and then we write v. So the way I say this out loud is I say u cross v. That's the way I say that x symbol. I say cross. And the cross product is a vector, unlike the dot product. The dot product, once I do it, gives me a scalar. Okay, so what properties does this vector have? So the first is the length of this cross product vector. So the length of u cross v is equal to the length of u times the length of v times sine of theta, where theta is the angle in between the two vectors. Okay, so I'm going to highlight this. This is an important formula for the length. And I'll draw a picture in a sec so we can see what this looks like, what u and v look like in relation to each other, and draw the theta in as well. Okay, so that's the length of this vector. So what direction is it going in? So this vector is orthogonal. It is orthogonal, and orthogonal is just another word for perpendicular. It is perpendicular to both u and v. So the cross product needs to be a vector that's orthogonal to both u and to v. Okay, so the third property is, well, if I were to think about a picture where I have, a plane, and in the plane there are these two vectors. There's a vector u, and there's a vector v. And then I want another vector that's orthogonal to both of those. It would have to be orthogonal to the plane. And if I want it to be sort of orthogonal to the plane, there's sort of two directions it could go. It could go sort of up perpendicularly to the plane, or it could sort of go down underneath the plane. So there's sort of two directions. So which direction are we going to choose? So that's based off of the fact that it will satisfy the right-hand rule. The right-hand rule, which we saw back in the first section of this chapter, 12.1, when we talked about axes in 3D space, the x-axis, the y-axis, the z-axis. And I mentioned then that the axes, their orientation needs to satisfy the right-hand rule for the cross product to work. So we'll see why in this section, but let's remind ourselves what the right-hand rule is. So there's sort of three steps to the right-hand rule. Okay, so the first is when we take the cross product of u and v, what we will first do is we'll point our fingers in the direction of the vector u, so the first vector that's written in the cross product. And then we'll curl our fingers in the direction of the vector v, so that's the second vector that's written in the cross product. And then when we do that, our thumb will end up pointing in the direction of the cross product vector of u cross v. Okay, so I'm going to draw a picture. So I'm going to draw a larger picture of that plane that we had. So I'll have a plane, and within the plane I'll have some vectors. So I'll have this vector u, and then I'll draw v also having the same tail. So I have this vector v, and then the angle between them, I'm going to call that angle theta. Okay, so this we kind of have to visualize a little bit. What would the right-hand rule look like? So I've copied the images from the textbook about the right-hand rule, although I think it's a lot easier to see it like in person if you have someone to actually show you what it looks like when you put your thumb, when you point your fingers, when you curl them, and when you stick your thumb out. So at this point, actually, what I'd recommend doing before I go further is there is a YouTube demonstration video of the right-hand rule that I will link in the description of this video, and I'll also post it in Camino. Pause this video, watch that demonstration of the right-hand rule first before I continue with this one. So I'll wait. So 4, 3, 2, 1, pause the video. Pause this video and watch that other YouTube video of the right-hand rule first. Alright, so hopefully you've done that. Hopefully you've paused the video and gone ahead and watched that other one. If not, really go ahead and do so now. It'll be really useful. Okay, so my picture is more like, so the version of the plane that I'm drawing is I'm trying to construct the cross product u cross v. The second picture has it in the reverse order, v cross u. And it turns out that the order does matter for the cross product. It makes a difference in terms of what the cross product vector looks like. Okay, so when I point my fingers in the direction of the vector u, when I point them this way, and then when I curl my fingers in the direction of v, my thumb will end up sticking straight vertically up. So that'll look something like this. So that's the cross product vector. It's going to stick up straight perpendicularly. Okay. It turns out that if we had done it in the opposite direction, if we had done v first and stuck our fingers out in the direction of the v vector and then curled them in the direction of the u vector, to do that I actually have to turn my hand upside down, and we'll actually see that in that video that I alluded to, this one here. So that's another reason to really watch that video. It's super short. Okay. All right, so let's continue. So that is what the cross product vector looks like. It satisfies that right-hand rule. Okay, so what are some properties of the cross product? Okay, so a number of these are kind of, I think, what we'd expect. So I won't just write them down because I think it's just more useful for me to just talk about the one that's most relevant to us. So the first property says that the cross product of two vectors is itself a vector. And that makes it different from the dot product, which outputs a scalar. The second property has one subtle but important thing, which is notice that there's a negative sign here. When you take the cross product of two vectors in this order, A first, cross B, that's the negative of the cross product of B crossed with A. In other words, the order in which you do the cross product matters. If you were to switch the order, you end up with the negative of what you would have gotten had you done it in the initial order. And we see that in this picture here. When you do U cross V, we got a vector pointing upwards. When we do the other order, V cross U, we ended up with the negative of that, so pointing in the opposite direction. Okay, and then properties 3 and 4 are, I think, what we'd expect to happen. So property 3 is a version of the distributive property, where we can distribute the A to the B and to the C here. Property 4 says if you have scalars K and L being multiplied by some of the vectors, you can pull them out in front of the whole thing. Okay, and then 5, I want to break down a little bit. This is saying that if you take the cross product of two vectors, that's going to be equal to the 0 vector. This green arrow means if and only if. What does it take for the cross product of two vectors to be equal to the 0 vector? So it turns out that A and B would need to point in either the same or opposite directions. And the reason why is if they're pointing in the same direction, that would mean that the angle between them was 0. If they were pointing in opposite directions, that would mean that the angle between them was pi. But in either case, whether the angle was 0 or if it was pi, it gives us the same sine of theta. Sine of theta would be 0 for both of these. Sine of 0 is 0 and sine of pi is also 0. So if sine of theta was 0, and going up to what we know what we had stated about the length of this vector, the length of the cross product vector. Well, if sine of theta on the right-hand side is 0, that means the length of our cross product is going to be 0. So the only possibility is for it to be the 0 vector. And that is where this fifth property comes from. Next, let's state the cross products of the coordinate vectors, I hat, j hat, and k hat. So cross products of coordinate vectors. So I'm going to begin by drawing a picture of our axes, so z-axis, x-axis, and y-axis. And I'm going to draw in the coordinate vectors. Okay, so some coordinate vectors, so I'll go I hat is in the positive x direction, j hat is in the positive y direction. Well, let's color that in more so it doesn't disappear like that. I hat, k hat is 1 up in the z direction. Alrighty. So if we were to take the cross product of I hat with j hat, now that you've paused the video to watch that video on the right-hand rule, actually no. This one, let's just say what it is together, and then for the other ones, I'll have you pause it. So I hat crossed with j hat, if we use the right-hand rule, is going to give us a vector that is orthogonal to these. And it turns out what that will be is, it'll be k hat. If I use the right-hand rule, and it'll turn out that the length of I crossed with j needs to be 1. And that's why it's just k hat and not something like 2k hat or 3k hat. If we use the formula for the length of I hat cross j hat, we'll get that the length is 1. And then also, it turns out that if you do j hat cross k hat, you get I hat. And if you do k hat cross I hat, you get j hat. And the order matters. So if you were to switch these, if you were to do the j, if you did j cross I, you would have gotten negative k hat. Okay, so one helpful diagram to visualize this is if you arrange the I, the j, and the k in this order, and you start making this circular diagram with arrows. What this says is if you were to take I cross j in that order, so I cross j going this way, what you'd get then is you'd get the vector k. And that's what this first equation tells us. And then the second equation tells us, well, if you do j crossed with k, then you end up with I. Okay, so that's what that diagram is useful for. All right, so I'm going to put this in a little cloud here. So if the axes don't satisfy, so now talking about the axes satisfying the right-hand rule, because the axes definitely do, they satisfy the right-hand rule, then I hat cross j hat would be equal to negative k hat. And conventionally, that's not what we want. If we have it set up like this, these cross products are so nice, it would be nice to be able to avoid things like negative k hats showing up. Okay, so we prefer this orientation so that it matches up really nicely with the cross product. This is why we require the axes satisfy the right-hand rule. In terms of our goals for this section, we have done goal 1, defining the cross product geometrically using this notion of length, the length of u times the length of v times the sine of the angle in between them, and then using the right-hand rule to determine what direction that it points. So in the next video, we'll talk about how do we compute the cross product algebraically using something called a determinant.